Okay. So welcome everybody. So the first speaker of this session is Guglielmo Nocera, who will give us a hammer chord blackboard talk on the exodromy theorem.
Yes. Online? Okay. Grazie. Okay, thank you so much for the invitation. Actually, the first time I was honored to give a talk at Ithaca was last year. And what I did last time is same thing I will do this time. Not the same content, of course, but the same strategy. So unfortunately, I don't really work in category theory. So what I did is take something from my research field. Notice that I used something in category theory, some categorical theoretic result to prove something, and talk about that. And of course, that's not a result of mine. So at the end, I will try to explain how that result somehow enters into my work. Good. So the title of the talk, let's try to do, is this a good, funziona come altezza? Okay. Title of the talk is the exodromy theorem and an application. So let us recall the following thing. So the base object in this discussion will be X, a topological space. Good. So definition, the category of presheaves over a topological space is defined as the category of functors from the category of open subsets of X to the category of sets. Good. What we'll do is to study some subcategories of this, so namely presheaves or sheaves with certain properties, and ask ourselves a particular question, which will come in a moment. So for example, so setting, so let X be a topological space, and suppose you have extra datum, extra structure. I will be more precise later. Now I'm just trying to converge to what I want. So for now, extra datum means mathematically nothing. Like, for example, what? So the datum of a closed subset. This is extra datum with respect to the original thing. Or what is called a stratification. Stratification is in some sense a generalization of this. So it's a system, a partition of your topological space into smaller spaces. Again, I will give the definition later. Or other things, a group action, so extra datum. What we will be interested in is this one. And then what can you do? You can do the following. You can consider, sheaves or presheaves on X with a certain property which, to be stated, needs such a datum. So, for example, sheaves with support in Z, or sheaves which are locally constant on X. There's no extra structure here. Or sheaves which are constructible over the stratification. These are the examples I'm interested in, and I will give definitions in a precise way later. So, examples, sheaves with support in Z, meaning that they are zero outside of Z, or what are called constructible sheaves or equivariant sheaves with respect to some action as well. So categorically, what we are doing is just considering a subcategory of this, where the property that cuts out the subcategory is, okay, to satisfy the scent, for example, that gives you a sheaf, plus to be constructible as many other properties. So we end up with something of this kind. P is your property. So one of these. X is your space. S is my extra datum. And well, you may also have a category of coefficients which generalizes this. So variation of this definition, so presheaves of X with coefficients in B, if B is a category. This is just functors from open of X to B. Just this. Okay, this was just an introductory part to give you the flavor of the kind of thing we're interested in. And to conclude this introductory part, the question. So what do I want to do with these subcategories? So question. Are there any cases of these geometrically relevant examples where this kind of thing, so presheaves with this very vague property, very undetermined property, with coefficients in this category, can I express this category in a way that resembles the bigger one? By this, I mean as a category of functors, where the target category is again B, and the source category is something else, something which is, of course, not open of X, is something more sophisticated, because it has to take into account the structure and the property, and which I will denote by X, A of X as P. So it's a new category that depends on it. But as you can see, this is non-trivial. So not every subcategory of a category of presheaves may be expressed as follows, at least in principle, because I am requiring that B stays the same. So I don't want the coefficients to depend on the original geometric datum, exactly as it's happening here. Sorry. Okay. Hey, this may seem like a vague question, but I think it will become clear later. And before diving into the theorems, let me just say one possible advantage of such a description, and a second advantage I will give at the end of the talk. So advantage of this. So why would I be interested in expressing a category of sheaves with some properties, again, in this form?
Sorry, can I stop you for a second?
Sure.
We want this, assume you have a solution to this problem. Assume you have a solution to this problem. You want this to be natural in B,
Yes.
or is it too strong?
You mean in B?
In B, yes.
Yeah, in B it's okay, but the real thing, which is not trivial, is also A to be natural in X as P in some way.
Of course, yes.
Actually,
Okay.
P is fixed, but in XS, yes.
Okay.
I will give an example. I think
Okay,
it will answer your question. But yes, everything would like to be natural, and the advantages I'm going to show, especially the second one, will take advantage of this naturality.
Mhm.
So yes, the question is perfectly fits perfectly in the setting.
Thanks.
And so yeah, the first advantage is that if B is, say, presentable, or something completely different, abelian, so an abelian category, or what is called a stable infinity category, which doesn't really, it's not of interest to us here, but so many possible important properties. Well, then, under the possible assumption, at least in this case, it's important that A is small, but usually everything is small in these kind of contexts. But then also our thing is, so also this category of pre-sheaves is if the answer is true, so also the category of functors. This is not completely obvious. And in general, it's not obvious how to prove such a statement, so that this thing is presentable, this thing is stable, and so on, if one doesn't have such a presentation. In particular, in the case of constructible sheaves, which I didn't define yet, but it's the case I'm interested in. Sorry, the way I convinced myself that it was presentable and it was stable in the stable case, and so on, was exactly this way. And there is also another application, which I will be more precise about that later, symmetric monoidality. So is the association XS going to this category in any way symmetric monoidal? This is interesting, actually. And so if I have the product of two topological spaces with two structures, how does it convert into, how does this kind of thing split into the two partial data of what I need? And in the case I needed, the answer was yes, thanks to this co-representability result. Good, so let us move to the actual part of the thing. So first example, first of two. Local systems. So let X be a connected topological space. A local system on X is a sheaf. So it's a pre-sheaf with the usual topology, so the topology of the space. Oh, sorry, for example, here I could have added a Grothendieck topology. This would be another extra structure with respect to which I can ask some properties to be true. So a local system on X is a sheaf over X, which is locally constant. Okay, that's the definition. I will try to write in the upper part of this. So the theorem related to this example is the following. The category of local systems over X, so this is defined as having as objects such sheaves, as morphisms of sheaves. And how does it compare to what we were saying? Well, S, there is no S here. There's just a space. But there is a P. P is exactly to be locally constant. So I'm considering, and also to have descent, so to be sheaves, not just pre-sheaves. Okay, so I'm considering the subcategory of this, full subcategory spanned by those objects which are sheaves and also are locally constant. So this is my category. This is equivalent as a category to something of that kind, and in particular to what are called the representations of the fundamental group of X, which I will denote by this. Okay, where this thing, I1 of X, as a category, this is a category, is defined as having as objects only one point, and as morphisms, so hom between the point and itself, is pi1 of X, the fundamental group, and composition is exactly multiplication, the usual thing you do with groups. Okay, and this is a result in topology that goes in that direction, right? Because the category A here depends on X, but the target category doesn't. It's actually the original category of coefficients. And actually, this can also be generalized to other categories of coefficients, for example, abelian groups or vector spaces. Okay, this is somehow a baby example. There's no S. This is what makes it more trivial in some sense. Huh. Okay. In the non-connected case, so when X is not connected, what appears here is the so-called fundamental group point. Now, let's move to the last part of the talk, constructible sheaves. So constructible sheaves are a generalization of what I called local systems, of locally constant sheaves. Let's give the definition. So definition, first part of the definition is, what is a stratification? So X, topological space. A stratification of X is a decomposition. So it's a family of Zi, with I belonging to some set of indices I. Each of one is a subset of X, which is locally closed. Sorry for so much topology. And okay, these are a partition of X, so that their union is so they are all disjoint, and their union is exactly X. Plus, there is some condition called condition of the frontier that I have to state. So essentially, for each I, the closure of I as a subspace is a union of strata, where those are the strata. So these are called, each one of these is called stratum. Okay, just forget it if you don't care. Okay, this is called a stratification. It's a partition, but it's a special kind of partition. Then I can define a constructible sheaf over X. So F sheaf over X, perhaps should, is called constructible if the restriction of F to each one of these things, the strata, so this is the picture, topological space partitioned in some smaller subsets. So the restriction to each one of these is locally constant. So it's a local system. So take the trivial stratification with only one subset, which is the whole space, and you get the previous definition. Okay, these sheaves form a full subcategory of the category of pre-sheaves over your space. And you may ask the usual question. So is this subcategory co-representable as such a thing? Again, in this case, B is the category of sets, but you can generalize this. It's not important now. And the answer is yes, which is the main thing I wanted to tell you today. Okay, let me just do this. So the exodromy theorem, today it's called the exodromy theorem. Actually, the actual exodromy theorem is a vast generalization of this, but so the theorem is that if, let me call the stratification S. Stratification S is this family. And it's the same letter I had used here. So it's the actual additional datum I am putting on my topological space. So if S is has some nice properties. So additional to the one I stated there. It's called conical stratification. It's not important here to specify what this means. Of course, you can ask questions. So if S is nice properties, then there exists such an A axis P. So it's called the category of exit paths associated to S, X and S. The P is implicit. I mean, I construct this because I want to deal with constructible sheaves, such that the category of constructible sheaves over X with respect to the stratification S, in the sense of that definition, is equivalent as a category as to fun exit XS set. Okay, so this is actually the basic formulation of this thing. The original proof that is not in this setting. It's in the, let me say, it's in the derived setting, but this is what interests us now. And that's a result going essentially in this direction, because it's exactly that kind of representation. Let me just conclude with the application. So what was the second advantage I was mentioning before? Well, you may take products of such stratified spaces. So it's like considering the Cartesian monoidal structure on topological spaces, but somehow lifting it to the category of stratified topological spaces. So you have a category of stratified topological spaces, just meaning a topological space with such a stratification. And you can take products of those. So you actually have a Cartesian structure. Then you can associate to such a pair, XS, this thing, constructible sheaves over XS. This is a category. It's convenient to see it as a presentable category. And in particular, it's going to live in the symmetric monoidal category of presentable categories with the tensor product, the co-complete tensor product. Okay. So one may ask, is this association symmetric monoidal? Well, if you are if you restrict here to conical stratifications, so if you are in this situation, then it's true. And for example, what a collaborator of mine and I proved, usual partner in crime for these things, is that the so-called Whitney stratifications fit into this context. Actually, that was previously known. What we did is something a bit more sophisticated, but it goes in that direction. And the answer is yes. You can actually prove, thanks to this thing. It's not completely obvious because you have to inspect how A works with respect to symmetric monoidality, and then you have to work with the notion of pre-sheaf. But you can then prove that this is actually symmetric monoidal. And this was something I really, really, really needed for my research, because I wanted to transport a monoidal structure, an algebra structure for my space in the stratified setting to the category. And if this is symmetric monoidal, Lex monoidal would suffice. You can transport an algebra structure here to here, which is what I needed for reasons I cannot expand now. Thanks.
Thank you. Is there any question?
Hi, thanks for your talk. So I guess we can think of locally constant sheaves as coverings of the topological space, right? And can I think of the exit paths category as some sort of gluing of the pi1 of the spaces in the stratification?
Yeah, actually, the symbol you use to denote exit, so Lurie used the symbol sing SX, meaning that it's actually some kind of generalization of the singular complex. So the list of essentially all homotopy groups. But of course, the stratification has to play a role there, right? It's the homotopy groups just don't see anything of the stratification. So the analog you're looking for is you replace paths, which are the thing that give you the fundamental group, with what are called the exit paths. So exit paths are paths that somehow play with the stratification. So exit means that they have to, where's the thing? So you replace the notion of path, which is gamma from I to X, which gives you the fundamental group, with gamma from I to X, such that for every, so if 0 goes to some stratum, then whenever the path exits, cannot come back. Where exits means go to, let me say, a higher dimensional stratum. It's not the correct notion, but that's it. So suppose you stratify with a line or a curve plus the complement. This is the small stratum, this is the big stratum, so your path has to go away. But to come back to your question, I think this is the actual analogy you use. So you mentioned the word gluing. I'm not sure I can interpret that, but at least
maybe I can justify my intuition. So you have your category of constructible sheaves, right?
Yes.
And by restriction, you can project over the local systems of each stratum.
Mm-hmm, sure.
So if you think of it, let's say,
I see. Yeah,
representably, then you get, well, I mean, you don't necessarily get those because...
No, now I got it, sorry.
Yeah.
Yes.
Yeah.
No, yeah, the gluing you're referring to is is related to the following problem. You have a decomposition of your space, not into two open sets, that would be, well, not a covering of open set, that would be gluing, but you have an actual decomposition in a closed subset and an open subset. So the fake gluing you would like to have in this thing is, I think, is called Rickle-Mann. And that's the answer to your question. Yes, it's related to this kind of problem, and it's a gluing of your data on the closed one and the open one, or on the stratification in the general case.
Okay, thanks.
Hi. On the properties, can you ask something about the geometry of X? I don't know. Not
What?
Among the properties, can you ask the extra datum?
Okay, yes.
Can you, I mean, does this give you something stronger when you X is some, I don't know, a complex variety? For instance,
Okay. So you mean for one of these particular settings, or in general?
Yeah, I don't know, because for instance, local systems are become very interesting by the Riemann-Hilbert correspondence, and
okay.
so I would imagine.
Yeah, I don't know if for example, the Riemann-Hilbert correspondence for constructible sheaves, for example, benefits in any way of this exodromy representation. We both know whom to ask, but I'm not sure. Maybe there is some simplification of things, not that I know of, but I may be wrong.
Okay, I think there is no time for other questions, so let's thank the speaker again.